Hello everyone and welcome to the last lab. So for the last lab of the course we're going to do power in AC circuit. It's quite significant, because the power in the circuits, it's a pretty critical thing in understanding the functions and then the translation into their effects in real world devices, right? And it's also important for logistics because the bills that the power company give you, those are actually based on the power used over a certain time, right? I guess it's the monthly period, let's say, not a voltage or a current number, obviously. So the real world circuits are actually based on AC circuit rather than DC. So today you have to simulate a couple of AC circuits and then you have to measure the powers in those AC circuits. And if you take the data accordingly and plot the phasor diagrams, you're going to be good to go. Okay? So that's what this lab is all about. So a couple of important things you've got to remember is that the power across a resistor, always in a circuit, if there is a resistor, the power across the resistor, that's going to be your active power, okay? So I'm going to show how to plot that. Then the power across the capacitor, that's going to be your capacitor or inductor. That's actually called reactive power. And when you have an inductor and capacitor both present in a circuit, which you're going to find in one of the circuit samples that I'm going to provide, that's going to be your reactive, for that, your reactive power is going to be the power of the inductor minus the power of the capacitor, okay? And the unit's going to be kVAR, okay? So then the apparent power this is how you have to find the apparent power. This is very important because when you have the inductor and the capacitor, or when you just have the capacitor, okay, or the inductor, whatever. So when you have a resistor, you have a capacitor in a circuit, then you're obviously going to need this formula in order to calculate this apparent power. And another thing to remember in mind is always the power factor, and this formula is pretty much straightforward. So S is the complex power, right? Or magnitude of the S is actually called the apparent power. So S is over here. So P is called the Pythagoras, just like Pythagoras theorem, P squared plus Q squared is equals to S squared. So that's what I did over here. So if I represent S as an apparent power, then P as the P active as active power, and then the reactive power is Q. Then that's what I just did, okay? And the power factor is obviously going to be from 0 to 1. It's not going to be more than that. If that's the case, then you're doing something wrong. And then when it comes to leading and lagging, so let's say you have a certain so how do you actually plot a phasor diagram? Or okay, so in that case, like whatever is leading, so let's say your voltage is leading, so your voltage is going to be on the left hand side of this, the factor from which it's leading. For example, your current is over here, your voltage is over here, and your voltage is leading the current by theta degree. In that case, this is how the graph should be. I mean, I just separated it out. I could have just plotted this as a lagging and this as a leading, so on, but I just tried to show this, just as a demonstration, okay? And then the circuits that you are gonna simulate today are these 6 circuits. So you're gonna see when you have the table, in the table you have 6 rows, right? So this 6 rows actually stands for this particular 6 circuits. So you're gonna have to simulate that. The values are properly specified, and then obviously JXL is J2 pi FL. The impedance of the capacitor is J2 pi FC, and how you're going to have to take the readings and everything you're going to see later on. And first you're going to have to see how to simulate the circuit, which I'm going to do in the next one. Okay, I'm going to show next. Okay, so I'm going to give you a demonstration of how to construct the circuit using fault step simulator, okay? So for the input source, it's going to be 2-terminal AC voltage source. Then I'm going to get a resistor. Make sure your terminals are connected properly, because if there is a bad connection or something, then it's not going to simulate, okay? You got to make sure about that. And if you press C, it's going to be capacitor. And W is for wire. So without wire, I can just click over here and then get the wire. Okay, so I'm gonna simulate circuit number 3. Okay, so for circuit number 3, basically, if you just have the capacitor, this circuit's not gonna simulate. It's a drawback of using this particular software. Okay, but we can see the waves and everything. So I'm just gonna make sure this is very, very small. So I'm gonna apply 10 volt, and this one is maximum voltage is gonna be 10 volts. And the frequency for United States it's 60 hertz. Then if I run it, you're gonna see this is running pretty smoothly, right? So now, how do I see the power across this 10 microfarad? So you gotta click view in new scope, and after that what's gonna happen is you click over this setting option and plot and then show the power consumed. Okay, so you can see, and then just stop it. So you can see the maximum power that it's transferring. It's 480 milliwatts, right? That means the reactive power for this capacitor is actually 480.58 milliwatts. So if I have my table over here, so I just want to demonstrate like how do I take the readings and everything. Okay, so for a capacitor it's always reactive power, so there's no real power, right? So for me real power would be 0, then the circuit current would be where is that? So what's the current, right? So in order to see the current, just take your cursor on the capacitor. You're gonna see 9.672 milliamps, right? So I'm gonna just give that as an input. 9.67 milliamps, and then the total circuit voltage, that's gonna be 10 volt obviously. Yeah, because we gave 10 volt as a maximum voltage, right? If you take a look at that, then you're gonna see, so maximum voltage is 10 volts. Okay, and now what is the resistor voltage? Even though the value, even though we have a resistor, the value of the resistance is very, very low, so we are not going to take that into consideration. Inductor value is 0. And then what's the capacitor voltage? The capacitor voltage across the capacitor, sorry, that's going to be, if I take my cursor on it, just don't click anything, you're going to see VD is 7.071. All right, sorry about that, 7.071. Now I'm gonna move over to table 2. So the VA, the circuit volt ampere, okay, circuit volt ampere is nothing but this voltage times this currents, so it's gonna be 96.7, right? 96.7. Now what's my W? W is the power, the real power or the active power of the circuit. So since it's just a capacitor, the real power is going to be 0, because I discussed before that the resistor's voltage, the power across the resistor, that's going to be your real power or your active power. Okay, so in this case you don't have a resistor, we just have the resistor just for the fact that that circuit is not going to simulate just with a pure capacitor. Okay, so power factor is obviously going to be 0. And reactive power, so the reactive power is nothing but the power across the capacitor. I guess we saw that, right? The power across the capacitor, this is 480.585. so now what is the impedance magnitude? The magnitude of the impedance is going to be, so the complex impedance, we know about the complex impedance, so it is nothing but what, the formula is J over XC, right guys? So JXC is, XC stands for 1 over 2 pi FC. So you know the frequency, which is 60 hertz. You know pi 2, you know the capacitor value is 10 microfarad. All you got to do is just calculate the capacitor, okay? And then what's going to be our impedance magnitude? So complex impedance in our case, we know it's going to be JXC, isn't it? So when we have the value, this is what the complex impedance is going to be. This is the real portion and this is the imaginary portion. So since this is just a capacitor, so the real value is going to be obviously 0. So if you take a magnitude of this, so the magnitude, since this is 0, so it's going to be what? Nothing, just XC, isn't it? And then what is the complex admittance? Admittance is something you gotta inverse this complex impedance and you just get complex admittance just like you did before, okay? And then if I go over here, the resistance value is 0, the inductive reactance is 0, inductance 0, capacitive reactance is what? It's JXC. You just have to calculate the value and then the value of the capacitance. What's the value of the capacitance? 10 microfarad, right? And now the thing is, over here they ask you to include a phasor diagram for each 6 circuits. So how do you do that? Okay, let's say that you have, okay, so over here you have a power factor. So power factor actually stands for nothing but it's actually you got to do the inverse of cos theta of this value. So the value of the power factor, like I said, it's going to be from 0 to 1, right? So for our case, it's 0 because there is no real power or active power over here. That's why we got 0, right? So when you do that, how much does that become? Cos inverse 0 obviously becomes 90 degree, right? So 90 degree means, so for a capacitor, what? The current leads the voltage, isn't it? And for inductor, the voltage leads the current. You know this factor. I hope I'm making this pretty easy. So that being the case, like I discussed before, so when you have a leading and lagging, let's say this x-axis represents voltage and your current is leading over here by 90 degrees. So your current is going to be along y-axis, right? That means your current, whatever is leading, that's going to be the arrow of the left, and the lagging one is going to be the arrow on the right. I mean the leading arrow is going to be obviously on the left hand side of this lagging one, okay? That's the basic thing. I mean the easiest way to remember it. So you do that, then what was the thing? Like we got cos 90 degree. That means this x-axis, if I make it, like it's not gonna be like I could make this over here or make this over here, right? All you gotta do is like make an anti-clockwise 90 degree leading for the current. So for this one, this is gonna be the voltage and this is gonna be the current, where for the capacitor the current is leading by 90 degree. It's pretty much simple, okay? So this is what you have to do for the rest of the circuits, and just start working on it, and that would be all. Good luck.